This is part 12 of the Module 11 lecture. In this part, we will look at an example of a complete regression analysis. This goes with section 13.5 in your textbook. All right. So to perform a complete regression analysis, you have to do these 8 steps. So number 1, you generate the scatter plot and interpret the relationship between x and y. If that relationship is that of a straight line, then you proceed. If it is not that of a straight line, then you need to stop and look for help, because fitting a more complicated model is outside the scope of this class. So here, all the examples that we use is where we can apply a simple regression model. Right, so you should see the points aligning on a straight line on the scatter plot. If that is the case, then we proceed to fit a simple regression model where we estimate or calculate the estimate of the intercept, lowercase a, and the estimate of the slope parameter, which is lowercase b, and we interpret each of these values. Then we write out the regression equation so we know what it is, because we will use it later. Then we calculate the standard deviation of the residuals, then calculate the coefficient of determination, r-squared, and interpret what this tells us. Then we proceed to test the hypothesis that the slope parameter is 0, and we calculate its confidence interval and interpret the results of that hypothesis test and that of the confidence interval. Then we use this sample regression model to make predictions and calculate the confidence and prediction intervals and interpret these intervals. And finally, we will construct the residual plots and interpret them to determine if the assumptions are met. All right, so this is what we will do to do a complete regression analysis. All right, to do this, we're going to use this example that comes from this book by Weisberg. And in this example, the physicist James Forbes, he wanted to estimate the altitude above sea level using the boiling temperature of water. He was interested in doing this because in the 1840s, transporting a barometer was very difficult. They were very fragile. So altitude can be determined from the barometric pressure. And as altitude increases, the barometric pressure decreases. And so does the boiling temperature of water. So to do this, he went to 17 places in the Alps and Scotland. And at each of those locations, which are very high, he measured the barometric pressure in millimeters of mercury, which is our y variable, and he measured the boiling temperature of water in degrees Fahrenheit, which is our x variable, and he applied some corrections for the environmental temperature, so those are corrected values. But anyway, we have that data, and we would like to use it to perform a regression analysis to determine if a straight line regression model or a simple regression model can be appropriate to predict barometric pressure from the boiling temperature of water. So to do this, we're going to use a 5% significance level and a 95% confidence level. All right, so step 1, we generate the scatter plot. But before I go into this, let me show you that we have an Excel worksheet posted on Blackboard that shows you all the things that we're going to do in this example. Let me go there so I can show it to you. All right, so in this table, if you click on the first tab, it just shows you the data, the temperature in degrees Fahrenheit and the pressure in millimeters of mercury. And then if you click on the scatter plot tab, it shows you the scatter plot that we will discuss in a minute. I show you all the calculations that are required. And again, if you want to see the formulas, click on the cells to see the formulas. So you can see how things are calculated. Oh, not there, but here. So you can see the formulas that used for these calculations. In the next part, this is the output that Excel generates if you use regression option under the data analysis, and the last tab shows you the different graphs. And if you click on the graphs, it shows you which columns are being used to construct each of the graphs. All right, so this spreadsheet is posted on Blackboard, and you can explore it on your own time. But now let's go back to the example and continue seeing how we do this a complete analysis. All right, so using Excel, I produce this scatter plot, and then if we look at it, the interpretation of it is that these points, they seem to align on a straight line. So it is reasonable to assume that we can fit a straight line model or a simple regression model to this data. All right, so we will proceed with the second step, where we calculate the least squares estimates of the intercept and the slope. For that, and again, this comes from Excel, you see that here's the original data, the temperature and pressure, and here's the product of the x times y, of temperature versus pressure. We get this number. Then the x variable, we square it in this cell, and the y variable, we square it in this cell. And we did that for every observation. Then we sum these quantities in each of these columns, and you get the different sums. These sums will be used to, for example, the sum of the x values is used to calculate the mean of the x values. The sum of the y values is used to calculate the mean of the y values. And then the sum of squares of the x-y product, when we use the different sums to calculate them as per this formula. The sum of squares of the x squares we calculate in this way. And the sum of squares of the y square values we calculate them in this way. So you see, this requires a lot of calculations. So in the final exam, what I will do is give you these results, and you'll start from there, so you don't have all these other calculations to do. All right, with that information, so we proceed to calculate the estimate of the slope parameter. And then by using this sum of squares, the ratio of this sum of squares, we find that B is 0.5229. So now we need to interpret what that means. So we said that on average, the barometric pressure increases by 0.5229 millimeters of mercury for an increment in 1 degree Fahrenheit in the boiling temperature of water. I use the word increases and increment. Why? Because this B coefficient of the slope is positive. So as the boiling temperature increases, the barometric pressure increases. So that's what this is indicating. And this is why we interpret it in this way. Now, then the intercept, you calculate it like in this way, and you find that is minus 81.0637. So to interpret this value, we'd say that at a boiling temperature of water of 0 degrees Fahrenheit, the barometric pressure would be minus 81.0637 millimeters of mercury. So in other words, we're saying if you were at a vacuum, because this is a negative pressure of 81.0637 millimeters of mercury, then water will boil at 0 degrees Fahrenheit. So again, we don't know if that is true because we never observed that data. So this conclusion may not have a real meaning. We will have to do the actual observation to see what the actual barometric pressure would be for 0 degrees Fahrenheit. And you won't find this barometric pressure in the ambient. You will have to create it somehow by evacuating some container. So again, this makes no sense, this interpretation. And we know that because we never observed that data. All right, so, but nevertheless, interpret it. And if it has not been observed, say that interpretation may not be meaningful because we never observed that data. All right. Then we go on to write the regression equation, the sample regression equation, and then we know in this case that the press is the short for pressure, and the hat symbol indicates that it's an estimate of the mean of all pressures measured for a particular boiling temperature of water. So that's what this equation will calculate. Next, we proceed to calculate the standard deviation of the residuals using results that we already obtained. If you apply those results into this equation, then you find that the standard error of the residual is 0.2328. Again, we don't interpret this result. This result will be useful later on. All right, so next we calculate the coefficient of determination. And then using these quantities, we find that the R-square is 0.9944. 0.9944. That means that the boiling temperature water, because it's the only variable in the model, explains 99.44 of the variation in the barometric pressure. So the remaining unexplained variation, 0.5 6% calculated in this way is very small and very likely due to measurement error. So we could say that the boiling temperature of water is a reliable predictor of barometric pressure. All right, so with that, then we move on to the next step. And now we test the hypothesis that the slope parameter is 0. And we calculate its confidence interval. All right, so we follow the 5-step procedure to test the hypothesis that the slope is 0 versus the slope being not 0. If it is 0, means that y does not depend on x. If it is not 0, then y depends on x. All right, so this is a two-tail test, a significant level 0.05. And then we rely on the assumptions of regression that the residuals are, that the random errors rather are independent, normally distributed with mean 0 and constant standard deviation, and that we're going to estimate the standard deviation of the random errors with the standard deviation of the residuals. Therefore, we can use the t-distribution with 15 degrees of freedom. All right, with that knowledge, we proceed to step 3 and calculate the test statistic, which is defined like as this. And we use the things that we have already calculated to test this hypothesis. And because under the null hypothesis, the parameter is equal to 0, well, that disappears from the numerator of the test statistic. So if you calculate this, you find that the t observed is 51.7408, a very large value. All right. Then you move on to step 4, and if you decide to use the critical value approach, then you go into table 5 with alpha over 2 and the 15 degrees of freedom, and you find that the upper critical value is 2.131. You find that directly on table 5. And by the symmetry of the t-distribution, we know that the lower value will be minus 2.131. So the rejection regions are for any t-value less than 2.131 or any t-value larger than 2.131. So these are the two rejection regions. Then if you are asked to use the p-value approach, again, you go to table 5, look at the row for 15 degrees of freedom and see where the t observed of 51.748 is. And you see that that's way beyond the largest t-value on the table, which corresponds to a probability to 0.01. So you can tell that the p-value is much smaller than 2 times 0.001. 2 times 0.001 because it's a two-tail test. And so, and if you calculate the exact p-value, it's practically 0. All right, so based on the fact that the t observed is very large, much larger than the critical value, and therefore lies in the rejection region, and also the p-value is much smaller than alpha of 0.05, then we reject the null hypothesis. So we say that the slope of the population model is not 0, indicating that the barometric pressure and the boiling temperature of water are related. The last thing we do is, again, use the assumptions under the regression analysis to justify the use of the t-distribution. We use table 5 to find the critical value, and then we use that number plus the other information we have, and we calculate the confidence intervals for the lower and upper confidence intervals, confidence interval limits of the 95% confidence interval for the slope parameter. So with these numbers, we say that at a 95% confidence level, the slope parameter is between 0.5014 and 0.544. In other words, that for an increment in 1 degree Fahrenheit in the boiling temperature of water, there is an increment in the population of atmospheric pressure between 0.5014 and 0.544 millimeters of mercury. And again, I wanted to remind you that the first sentence here, it is the correct interpretation of the slope parameter, but don't stop there. Use your knowledge to extend that interpretation to a practical interpretation, as we did here. All right, so I will stop here, and in the next recording, we'll continue with this example.